see that again?
If you get a significant value for the interaction between the input variable 1 and input variable 2, does that mean that both of those together, what's your seeing?
Right, so when you have an interaction, it means that some combination of IV1 and IV2 caused a significant difference, but it had to be that combination. Not one of them will be independent. All right, so here's what that would look like, what those data would look like if we graphed them. You guys remember what the graph looked like last time? Let me go back here. So remember this graph? That was the first graph we looked at. And I told you that we can look at graphs and we can get a sense of what's happening with the math by looking at the graph. So when we're looking at a graph and I want to know if there's a main effect of the variable on the legend, excuse me, the variable on the x-axis, okay, this one down here at the bottom. If I wanted to see if there's an effect of that variable, and I've got a line graph, I'm going to look at the slope of the line. And so because these lines have a slope that's not 0, there's a possible main effect of the variable on the x-axis. If the lines have a slope that is 0 or close to 0, there's no chance of there being a main effect of that variable. So when it comes to the variable on the x-axis and line graphs, we care about the slope. The steeper the slope, the bigger the effect. When we're interested in figuring out what's happening with that variable in the legend, and we've got a line graph, we focus on how far apart the lines are. The further apart the lines are, the bigger the effect. Right? They might be a little bit apart, but that would be a really, really super small treatment effect and probably wouldn't be significant. The further apart they get, the more likely that difference is to be significant. So we have a possible main effect of alcohol here. When we want to know if we're looking at a line graph, if we have an interaction, we focus on whether the lines are moving towards each other, touching, or crossing. So they don't have to cross, they don't have to touch, but if they're clearly moving towards each other, the extent to which they're doing that, if they're like going right at each other like that, that's clear indication that you are likely to have an interaction. If the lines are parallel and there's no way that they will touch or cross, not a hint of it at all, then you are sure you don't have an interaction. You can think of interaction when two things interact, what does it do? Right? They come together. So interaction and intersection work together. You can think of those two things together. Okay. So now let's take a look at the data that you guys did math for today. Here they are graphed in a line graph. The variables are on the same axes. How is this graph different than what you saw before? So no alcohol doesn't have as much of a slope, but alcohol has more of a slope. Okay? What's that about?
The effect is going to be more for alcohol.
Well, what did we just say? These lines aren't parallel anymore. What's happening?
They're going to interact.
They're coming together. So we've got an interaction here that we didn't have in the other data. Okay. These lines are coming together, and as they get closer, as they get over to the right side of the graph, they're getting closer and closer and closer. They're not touching, they're not crossing, but they're still getting clearly closer and closer together. So we've got a chance at an interaction. That's the math we did where we had 80 and what were the numbers? 80 and 50 and 20, right? And I said, well, it depends on, it depends on what our critical value is. But the fact that those numbers were different tells us that we have a possible interaction. It matters what our critical value is, but we've got this interaction here, or possible interaction here. Now, what's challenging about having an interaction is that it makes it harder for you to know what's going on with the main effects. And that's because, well, let's think about it. I told you that on the x-axis, what we focus on with the line graph, if we're trying to figure out if there's a main effect of that variable, is the slope of the line. And as you pointed out, Well now, the no alcohol line has less of a slope, but the alcohol line has more of a slope, right? That's because of the interaction. So the interaction is skewing the cues that we use to figure out if there's a main effect on that variable. Okay? The presence of the interaction is messing with our visual cues. So could be, I mean certainly these lines are not flat, and one is less not flat than the other. But it means that while we might report that there's a possible main effect of the variable on the x-axis, we want to be cautious in interpreting it because it's possible that the appearance of that main effect is an artifact of the interaction and not reflective of an actual impact of that variable on the dB. Now if we think about the cue we use to tell if the variable in the legend is significant, right? That's how far apart the lines are. Well, again, the interaction messes with our cue because at the left side of the graph, they're really far apart, further apart than they were in the other graph. And at the right side, they're really close together. So are they far apart or not? Well, it kind of depends where you are in the graph. That's basically what an interaction is, right? It depends what special combination of variables you've got. But because we're getting a really strong message at one side of the graph and a really weak message at the other end of the graph, we can say, well, there may be a main effect of the variable in the legend, but we have to be cautious because it's in the presence of an interaction. So what I want you to remember is that when we're analyzing data with the factorial design, what we care about most, what we have to think about first, is whether or not it looks like there's an interaction. And that's because the presence of an interaction can obscure or distort main effects. Now, if we're pretty sure we don't have an interaction, we're going to go after those main effects and interpret them vigorously. But in the presence of an interaction, we have to be cautious about main effects because they could reflect type 1 error. The lack of a main effect could reflect type 2 error. That's occurring because the other variable is present. So if you get factorial data or you get a graph, look to see if there's an interaction. If you get an interaction, great. Describe that interaction. If you don't get an interaction, go ahead and look for main effects and then describe those main effects. It's fine to talk about main effects in the presence of the interaction. You just want to be careful about putting too much weight on them because those main effects could be skewed by the interaction. So it's okay that they're there, but you just want to be careful. Now, when we're doing factorial analysis, it's possible to have any combination of interactions and main effects. You can have everything be significant. So you could have a statistically significant effect of IV1, main effect of IV1, a main effect of IV2, and an interaction of IV1 and IV2. That's totally fine. You could have a main effect of IV1, no effect of IV2, and no interaction. Like any combination of those things is possible. So you don't know, if you get one of those calculations turns out to be statistically significant, that tells you absolutely nothing about whether the others are significant. Nothing. So you always have to do the math for all of them to know what your observed values are. And you always have to compare it to a critical value to decide whether or not it's significant in all the cases. And it's possible you could end up where you do the math and nothing is significant. That's possible too. 3 different F-tests, each one independent of the others, and you have to do the math for all of them. Let me ask you a question. Say we have, you know that if we have 2 IVs, IV1 and IV2, you know that we can have a main effect of IV1, a main effect of IV2, and we can have an interaction of those 2. What happens if I have IV1, IV2, and IV3? How many main effects can I have?
3.
3, right? 1 for each IV, right? Okay, so I can have 3 main effects. Possibly. 3 possible main effects. Because I could have 1, 2, or 3, right? Or none. How many interactions can I have?
3, 4.
3, 4, which is it?
1, 2, 3. 3.
Okay, what are those interactions?
IV1, IV2, and then IV2, IV3, and then IV1, IV3.
Goes back to that.
Can you have an interaction between IV1, IV2, and IV3?
Yes, you can. So, we go by adding a single independent variable, we go from having 2 main effects and 1 possible interaction to 3 main effects and 4 possible interactions. That's why a lot of people don't do experiments with 3 independent variables, because then you've got a whole lot of math. And even if you're running all the math on a computer, explaining and interpreting all of those main effects and interactions takes forever. That's why lots of research articles are like 47 pages long. You have to explain all that stuff. Okay, so if you have, when you have a factorial design, you have possible 1 main effect for every independent variable and 1 interaction for every possible combination. Okay. Let me note that there is no difference between saying IV1 and IV2 like this, or IV2 and IV1 like that. Although nobody would ever do it that way. We always put the lower number first. But those are exactly the same interaction. So you don't need to say, oh, there's IV1 and IV2, and that's different from IV2 and IV1. We're not counterbalancing. So you don't have to, the order makes no difference. So you don't have to say that. All right, does anybody have any questions about that stuff? You ready to look at some graphs? Lots and lots and lots of graphs. Well, whether you're ready or not, that's what we're going to do. So I hope that you got the handouts down here, because you will definitely want to have them, because there are lots of graphs and you will not want to draw all these graphs. Okay, so what we're going to work on now is learning to recognize the phenomena we've been doing math for in a visual representation. We've been doing t-tests, f-tests, t-tests. We've been testing things for effect size. Now we're going to look and see what these things look like when we put them in a graph. Because papers almost always have a graph of the big result. You know, if you read Stansbury and Monroe, there's a graph of the big result. And very often when people don't want to look at all those APA-style statistical statements, what do they want to look at? The graph. So I want to make sure you know how to look at the graph and tell what's going on, understand the connection between that graph and the math. Okay? So I'm going to present you with there's an experiment. And this experiment, we've got 1 independent variable that is beverage. And the levels are alcoholic and non-alcoholic. So people in this study either got an alcoholic beverage or a non-alcoholic beverage. They could not tell the difference between the two. The second variable is expectation. And people were either expecting alcohol or not expecting alcohol. So they were either told they were getting alcohol or told they were not getting alcohol. So this is a 2x2 design. How do I know that? 2 levels on each one. There's 2 variables. and there's 2 levels on IV1 and 2 levels on IV2. So that's the 2 by 2 design. Okay, how many different conditions do I have?
Or
4. What are those 4 conditions? Alcoholic, people who got an alcoholic beverage and were expecting it, people who got an alcoholic beverage and weren't expecting it, people who got a non-alcoholic beverage and were expecting it, or non-alcoholic beverage but were expecting to get alcohol, and people who got a non-alcoholic beverage and were not expecting to get alcohol. Okay, so those are the 4 different groups of subjects in our study. These are both between subjects variables with random assignment. The variable is manipulated. The researchers have complete control over this. They can randomly assign subjects to the groups. So if this it's a 2 by 2, both are between subjects, both are manipulated, random assignment was used, what kind of factorial design does this have? It's a 2 by 2, what factorial design? Flowchart. Random groups factorial design. Yes, that is exactly right. Okay, so we've got a 2 by 2 random groups factorial design with one of the variables being the beverage type, the other variable being expectation, and our dependent variable is intensity of shock. So people were given a beverage, they drank a certain amount, and then they were given the opportunity to shock, although not really shock a Confederate they thought was a real person who was making mistakes like spelling words or something. So what we're looking to see is, does whether or not you got alcohol affect how much you shock? That would be the main effect of beverage. Is whether or not you're expecting to get alcohol affect how much you shock? That would be a main effect of expectation. Or is there a special combination of those 2 things that leads you to shock more or less? And that would be the interaction of beverage and expectation. So I'm going to show you a whole bunch of graphs which are all different possible outcomes for this experiment. We're going to look at both line graphs and bar graphs, and we're going to learn how to interpret these graphs just looking at the visual cues present in the graph. Now we did one like this a little bit ago at the beginning of class. We were looking at the different graphs for the data we had done math for. So let's see if we can apply those same principles to this line graph. When we talked, first we want to say, do we have an interaction? Because remember, we hear lots about interactions. How can I tell if there's a possible interaction in these data? Whether they intersect, what else? What else can suggest, aside from actual intersection? Well, they can be
The distance between?
Remember that it's not just whether they touch. They don't have to touch for there to be an interaction. They need to be moving towards each other, right? Clearly moving towards each other. Moving towards each other, they can touch, they can cross. Okay? Touching and crossing mean you got, if they definitely touch or they definitely cross, you've got an interaction. Okay, for sure. If they touch or cross. But even if they're just moving towards each other, very clearly moving towards each other, then you've got a possible interaction. Okay. Does it look like these lines are moving towards each other, are touching or crossing? No. No, these are parallel, right? So what's the chance that we have an interaction here? 0. There's no chance of an interaction. None. Because parallel lines means no interaction for sure. To the extent that the lines move towards each other, the effect size of the interaction is getting bigger and bigger, right? And particularly if it's really extreme on one side and together on another side or crossing, then you've got like a huge effect. So we don't have an interaction. Okay, that's good. Now let's take a look for main effects. Main effect of the x-axis. We make that determination by looking at the slope of the lines. Okay? If the slope of the lines is 0, then definitely no main effect. To the extent that the slope deviates from 0 in either direction, positive or negative, we have a potential main effect. So if I look at the lines on this graph, what do you think the likelihood is that I have a main effect of beverage? 0. Those lines are completely flat. Okay? Slope of 0. Nothing's happening here. Okay? It makes absolutely no difference whether people had a non-alcoholic beverage or an alcoholic beverage. Makes 0 difference. Those scores are exactly the same for those two categories. So we have no main effect of beverage. Makes no difference whether people got alcohol or didn't get alcohol. They shopped exactly the same amount. When it comes to the y-axis, what we pay attention to is how far apart the lines are. The further apart the lines are, the bigger the treatment effect and the more likely we are to have significance. Do these lines look very far apart? They're basically as close together as I could get them so that you could actually see there are two different lines on the page. Okay? They're super close together. The chance of us having a main effect of expectation here is extremely small. I would say that it's unlikely that there is any kind of main effect of expectation. It does not matter whether people thought they were going to get alcohol or not get alcohol. They pretty much behaved exactly the same way because those lines are super close together. Does everybody understand that interpretation? So we've got no main effect of beverage, no main effect of expectation, and no interaction. This is the big nothing. And the graph is boring because the findings are boring. There's nothing going on here. Nothing happened. This is retain the null hypothesis for all three tests. Yawn. Super boring. Now, we don't always get line graphs, though. Sometimes we get bar graphs. So it's not good enough for you to be able to read a line graph, because sometimes line graphs aren't appropriate for the data.
They're not as fun.
Huh?
They're not as fun.
Well, it depends. Sometimes line graphs can be super fun, but bar graphs are also cool. I like bar graphs more personally. So this is a graph, a bar graph, of the exact same data. Okay, exactly the same. So last time we looked at those lines. We said no main effect of expectation, no main effect of beverage, no interaction. Okay, these data show that exact same pattern. But now I'm going to explain to you how you know that. Okay, what kind of cues do we use when we're looking at a bar graph? So first, how do I know that there's no interaction? Well, when I'm trying to figure out if there's an interaction, I have to take into consideration all the different combinations, all the different conditions. Okay? So I have 4 conditions here. I've got non-alcoholic beverage but expecting alcohol, non-alcoholic beverage not expecting alcohol, alcoholic beverage expecting alcohol, and alcoholic beverage not expecting alcohol. Okay, I'm going to take into consideration all 4 of those bars as individual units. Okay, and here's what I'm going to do. I'm going to look for the pattern of difference and direction. So first thing I want to do is look and see over here, how different are the bars here? Okay, they're different by a small amount. Okay, very small amount. Looks like if I compare it over here, it's less than 5 volts. Okay, they're not very different at all. The difference is about that much. Okay. What's the direction of that effect? The direction is the black bar is taller than the white bar. Okay. So the difference is very small, and the direction is black taller than white. Now what I'm going to do is I've considered these 2 bars together, and I'm going to look at the next 2 bars. And I compare it here. What's my difference in direction? Well, the difference is very small, and the direction is black is taller than white. So in these cases, I've considered all 4 bars now, and the difference is the same, the direction is the same, and that means no interaction. If the difference and the direction are both the same, you do not have an interaction. There's no interaction here at all. So now that there's no interaction, I'm going to go take a look at the main effects. First, let's look at the main effect of beverage on the x-axis. What are the groups I'm comparing when I think about beverage? What are the different types of beverage in my study? Alcoholic and non-alcoholic, right? Okay. So that means I want to think of two groups. Okay, there's just two things I'm comparing now. I'm comparing the non-alcoholic bars with the alcoholic bars. So in your head, imagine one gray bar, that's the fusion of those two things together, and a gray bar, that's the fusion of those two things together. Okay, imagine that in your head. Do those two gray bars look about the same? Yeah. And that's because there's no main effect here. It doesn't matter whether you got non-alcoholic beverage or an alcoholic beverage. The combination of these two together and these two together gives me basically the same thing. Does that make sense? So we're looking at a main effective beverage. We just need to think about the alcoholic bars as one thing and the non-alcoholic bars as one thing. Yes?
Well, one step, like you said, so if the direction and difference are the same, then there's no
interaction.
No interaction. So with the black taller than white, that's just like how much taller it is than the white, and that's what makes it the same, or?
So it's two factors.
Right.
It's which one is taller and how much taller is it.
Okay. Gotcha.
So you have to have both of those things be the same for there not to be an interaction. If the difference, if one is, it could be that black is taller than white, but in one case it's this much taller, in another case it's this much taller, the direction would be the same, but the difference would not, and you've probably got an interaction then. Could also be that you have one bar is taller than the other bar by this much, and in the other set, one bar is taller than the other bar by this much. But in one case, the black bar is taller, in the other case, the white bar is taller. That would also be an interaction. So when you're looking for interaction stuff in bar graphs, you need to have both the difference and the direction be the same to be confident that there's no interaction. And we will see pictures of that in a minute. Okay. I'm going to give you every possible combination so you will have a model for every possible combination. Okay, so no main effective beverage. And we know that because this gray lump in our heads is the same as this gray lump, basically. All right, now, if I want to figure out if there's a main effect of the variable in the legend, what are the two categories that I'm comparing for the variable in the legend? Expecting alcohol and not expecting alcohol, right? Because the variable in the legend is expectation, and its two levels are expecting alcohol and not expecting alcohol. Okay? What do those two variables look like on the, those two levels look like on the graph? No, what do they look like? Give me an adjective, like a color.
Black.
One is black and one is white. Okay? Before when we did the other one, we were thinking about gray blobs, right? Now we're not thinking about gray blobs, we're thinking about black blobs versus white blobs. Okay? So imagine putting the two black ones together, making a blob. Put the two white ones together and make a blob. Are the black blob and the white blob about the same?
No.
The black blob is a little bit different, right? It's a little bit bigger. And the white blob is a little bit smaller. Then the question is, do you think it's enough different that it's an effect, or do you think it's just a numerical difference? Like error, measuring error. It's a really tiny difference. And I promise I will give you nice big differences if it's really different. So even if it's a tiny bit different, we're probably talking about a numerical difference. So the black blob is a little bit bigger than the white blob, but the important thing here is that it's just a little bit bigger. So there's a very, very small chance that there's a main effect, but probably not, because it's so tiny. There's a numerical difference, but it's probably not statistically significant. So let's think about that again. So for the interaction, we're considering difference in direction of these two compared to difference in direction of these two. So we're considering all four things independent. When we're thinking about main effect of whatever is on the x-axis, it's gray blob versus gray blob. When we're thinking about the main effect of what's on the legend, it's black blob versus white blob. Okay? You're trying to be visual about it. All right. Here's another line graph. Different pattern. So let's think back to line graphs. Okay, does it look like we might have an interaction? Yes or no?
Yes.
What does interaction mean? When things interact, what happens?
It
They
touches-
come together, right? So, interaction, in order to have an interaction in a line graph, they at the very least need to be moving towards each other, and typically with some vigor. Okay? If they are actually touching or crossing, then yeah, for sure you've got one, but to the extent that they are moving towards each other, you can say there's a possible interaction. These lines are not moving towards each other at all. Okay, they are parallel. Doesn't matter how far we go, they will never touch. So there is no interaction here because the lines are parallel with each other. They're not moving towards each other at all. If they're moving towards each other a tiny bit, could be, but you really want to see them like seriously moving towards each other, maybe even almost touching, maybe touching. That's what an interaction looks like. All right, so no interaction. All right, so let's think about the main effects. What do I consider when I'm trying to decide if there's a main effect of what's on the x-axis? The slope. Okay? If there's no effect, the slope's going to be 0. And to the extent that the slope is not 0, I've probably got a significant main effect. So what's the slope look like of these lines? 0. It's looking pretty 0. Yeah. So do I have a main effect of beverage? No, it makes absolutely no difference whether people got alcohol or didn't get alcohol. They shock the exact same amount. All right? So what about the variable in the legend? The variable of expectation. How do I tell if there might be an effect of expectation, whether people were expecting alcohol or whether they weren't expecting alcohol? How can I tell? How close the lines are, okay? How close are they? Are they like right on top of each other like they were before? No, they're separate. So if the solid line is people who were expecting alcohol and the dashed line is people who were not expecting alcohol, what does that main effect look like? Can you tell me? There was a main effect of expectation such that what? People who were expecting alcohol did what? Shocked more than people who were not expecting alcohol. So basically, people who thought they were going to get drunk were meaner than people who didn't think they were going to get drunk, regardless of whether or not they were actually drunk. Isn't that nice? So basically like, all right, I'm drunk, I can blame it on the alcohol, right? I think there's a song about that, right? This is basically the blame it on the alcohol graph. If I think I'm drunk, then I can do whatever. If I think I'm supposed to be drunk, then it's not my fault. I can shock away. But if I think I'm not supposed to be drunk, then I'll be good. Isn't that nice? Blame it on the alcohol graph. All right, so we've got no interaction, no main effect of beverage, and possible main effect of expectation. Okay. You see that? You see that, Corey?
I guess what's confusing me is how you would plot the actual data points.
How I would what?
Plot the actual data points.
Those are them plotted right there.
I was like, is this really numbers like if you're expecting to drink but you actually aren't drunk, like how that would gather the data look like? If I get the information that you're giving.
What do you mean? So what they did was they had people in each of these different conditions, right? Some number of people, 15, 20, 30 people in each of these conditions. And they gave them the opportunity to shock people and then calculated their average shock once they had the beverage that they were supposed to have. And each one of these dots, each one of those represents a grand average. It's like a number in one of the boxes that I give you, where you do the math. That's just the number converted into a picture. Does that make sense? So here's the exact same data, but now presented in a bar graph. Exact same data. So, first question, do we have an interaction?
No.
Same data, data hasn't changed. There was no interaction last time, there's no interaction now, right? But the question is, how do we know?
The distance and the direction.
The distance and the direction are the same. Can you walk me through that? So the difference in the direction, the difference, what the difference between what and what?
The difference between expecting alcohol and not expecting alcohol is the same.
On the left, right? So we have the black bar is twice as tall as the white bar, right? Over here, and that same pattern holds over here. The black bar is twice as tall as the white bar. So the difference is the same, this much, and the direction is the same, black is taller. Does that make sense? Okay, so no interaction. Difference in direction are the same. Main effect of beverage. Okay, this is gray blob here compared to gray blob here. Do you think those two gray blobs are the same or different? Same. No main effect of beverage because the gray blobs are the same. For the for the legend variable, we're comparing black blobs versus white blobs. Do you think the black blobs would be different in size than the white blob? The black blob, if I took the two black bars and mushed them together into a blob, would that be a different size than the white bars mushed together into a blob? Would be twice as big, right? That's the main effect of expectation again, right? That's the people who are expecting alcohol shock twice as much as people who are twice as high as people who are not expecting alcohol. It's to blame it on the alcohol condition. All right, here's another graph. Different outcome. Okay, does it look like we have an interaction? Why not?
They're still parallel.
Yeah, they're parallel. These lines are not moving towards each other. They are not intersecting. They are not touching. They aren't crossing. These lines are parallel. No interaction. So we'll just set that aside. No interaction. I feel good about that. What about the main effect of the variable on the x-axis? What do you think? Is there a main effect of beverage? What makes you think so? The slope of the line. Look at how steep that slope is. That slope is definitely not 0 anymore. What's that? Can you describe that main effect for me? There's a main effect, a possible main effect of beverage such that, what? People who got an alcoholic beverage did what?
Delivered more shock.
Delivered more shock than
Those who did.
those who got a non-alcoholic beverage. Right? Can you see that? So instead of looking at the numbers, we're going to look at the picture and come up with the same kind of description. Right? What about the main effect of expectation? Do you think we have one?
No.
Why not?
Because the lines are close to each other.
The lines are very close to each other. So they're clearly numerically different, but whether that difference is big enough to be significant seems unlikely, right? They're still pretty close to each other. This looks a lot more like Dr. Darnell was trying to show you that there were two lines and knew that it was not only going to have to be projected up here on the big screen, but it was going to have to get shrunk down into a little tiny graph on your paper, and if it was much closer together, it would basically blur into one line. So no effect of expectation. Did not matter whether you got a non-alcoholic beverage or an alcoholic beverage. It didn't matter whether you were expecting alcohol or not expecting alcohol. What mattered was whether you got an alcoholic beverage or not. And in this case, the people who got drunk shocked more than the people who were sober shocked less. Okay, so it's not about expectation, it's about whether or not you were actually drunk. So this is the mean drunk graph. Right? Drunk people shock more, sober people shock less, regardless of whether they think they're supposed to be drunk or sober. Okay, here's what that looks like in a bar graph. So, interaction. How do we know there's no interaction here, aside from the fact this is exactly the same data we decided in the last graph there was no interaction? The difference in the direction, right? Or distance and direction, that's fine too. Right, so here, black is a tiny smidge taller than white. Little tiny bit. And what's true up there? Black is a tiny smidge taller than white. Same difference, same direction, no interaction. Same difference, same direction, no interaction. Okay. What about the main effect of beverage? Does it look like it mattered whether you got a non-alcoholic beverage or an alcoholic beverage? Yeah, we're thinking about this gray blob over here on the left. We blended those in our head. Gray blob on the left compared to gray blob on the right. Gray blob on the right is going to be ginormous, right, compared to the one on the left. So it definitely mattered. People who got an alcoholic beverage shocked a lot more than people who got a non-alcoholic beverage. Okay, now if we're looking at the variable in the legend, black versus white, what happens if I take the black blob, the black bars and mush them into a blob, and compare it to the white bars and mush into a blob? Hmm? It's about the same, right? I mean, the black one's going to be a little tiny bit different, but not too much. There's a tiny numerical difference. It's very unlikely that that's enough of a difference to count. So probably no main effect of expectation. It doesn't really matter whether you think you're going to get alcohol or you think you're not going to get alcohol. What really matters is whether or not you did get alcohol. And if you did, you were shocktastic. And if you didn't, then you were relatively nice. All right, back to line graph. Interaction? No. What do I need to know for an interaction? Are they moving towards each other, touching or crossing? Are these moving towards each other, touching or crossing? No. So, do I have an interaction? Even a possible one? No. Because they are not moving towards each other, touching or crossing. No. Okay, so what about the x-axis? An effective beverage. Does it seem to matter whether people had a non-alcoholic beverage or an alcoholic beverage?
Yes.
Yes.
Yes, it does seem like that mattered. How can you tell? Not the space. The slope, right? It matters that the lines are not laying flat parallel to the x-axis, right? These lines have a clear slope. And can you describe that main effect for me?
The ones with more alcohol delivered more intense shots.
People who got, it's not more alcohol, but people who got an alcoholic beverage shocked more than people who got a non-alcoholic beverage. That's that main effect. What about expectation? Do you think there's a possible main effect of expectation? Maybe. Why? Because the lines are a little bit apart. They're not super far apart, but they are some apart. So there's a possible main effect of expectation. What is that effect? Can you describe the effect to me? If the solid line is expecting alcohol and the dashed line is not expecting alcohol. So can you describe it to me? There's a possible main effect of expectation such that what? People who were expecting alcohol did what? Delivered more shock than who? The people who were not expecting alcohol. Yeah. You still have to be able, remember, it's our same thing. What groups are we comparing? What do we compare about the groups? Was it significant or not? But in this case, it's whether we think it could be significant and the direction of the effect. So all of that has to be understood. Okay, here's that exact same data, but in a bar graph. So, how do we know that there's no interaction here?
Because there's a difference in the direction.
The difference in the direction is the same. So, the black bar is about, looks like it's about 20, maybe 30 volts higher than the white bar. And that's true on the left and the right. The difference between the two bars is about 30 volts, and the direction is always black is higher than white. So difference in direction are the same, no interaction. Next, main effect is a variable on the x-axis. That's gray blobs. So I'm comparing the gray blob on the left to the gray blob on the right. Are they going to be different? Yeah, the gray blob on the right is going to be a lot bigger, right? Because there's so much more stuff going into it. It's going to be a really big gray blob. The one on the left is going to be smaller, much smaller, because there's so much less going into it. So main effect of beverage. And about expectation, we're comparing black blob to white blob. What do you think? Black blob is going to be bigger than the white blob, so possible main effect there. Oh no. Now everything has changed. Corey, you trying to figure out how long you have to suffer in this class still?
After class, lab.
Yes, lab. Enjoy lab.
Please on us.
Hey, that's fine. Lab, you get a lot of stuff done in lab, I promise. Okay, so does it look like we might have an interaction?
Yes.
Yes, how do you know?
They look like they're going towards each other.
They're moving towards each other, right? At one end of the lines, they're closer together. At the other end of the lines, they're farther apart. So it looks like we have a possible interaction of beverage and expectation. Now, when you have an interaction, you want to describe it. One of the easiest things to do is to look and see if there's one group that stands out from all the other groups. It's kind of like that Sesame Street thing. One of these things is not like the other, right? You have to figure out which one is different. So if you look at these 4 conditions, which one seems the most different from the others? Expecting alcohol and drank alcohol. Okay, so the condition where they were expecting to get alcohol and they got alcohol. Right, so these are the people who thought they were going to get drunk and they got drunk. And those people administered the highest shock. So if you wanted to describe this interaction, you could say there was an interaction of beverage and expectation such that participants who got an alcoholic beverage and were expecting an alcoholic beverage shocked the most of all the groups. So you kind of pick out the one that seemed kind of extreme and describe that one to me. Now, given that there's an interaction, that's going to mess a little bit with the cues that we use to figure out about main effects. So that's why we want to look. So now we know that these other cues, we want to definitely be cautious when we describe the main effects, if there are any, because it's possible that any main effects we observe are artifacts of the interaction. It's also possible that if we think there's no main effect, that's also an artifact, because remember, interactions have the ability to distort or obscure main effects. They reduce the statistical validity of main effects. All right, so if we want to figure out if there's something happening for beverage, we would look at slope, right? Now, these lines are not flat, but one of them has a steeper slope than the other, right? Because they're moving towards each other. So we can still say that they're not flat. They definitely both have a slope that's not 0. So there's a possible main effect of beverage. And it's always the case that the alcoholic end is higher than the non-alcoholic end. So we can still say that there's a possible main effect of beverage such that people who got alcoholic beverages shocked more than people who got non-alcoholic beverages. That's the general trend. And if we look at the thing on the y-axis, right, what we're looking about is how far apart the bars are, the lines are. And the problem here is that they're far apart on one end and close together on another end, but they're still not right next to each other. So we can say there's a possible main effect of expectation. And in general, people who were expecting alcohol shocked more than people who were not expecting alcohol. So there's a possible main effect there. We're just less excited about these main effects because we're not sure the extent to which they've been influenced by that interaction that we see. So we just want to be cautious. All right, here's what an interaction looks like in a bar graph. One kind of interaction. Right? How do I know there's an interaction in this graph? The difference is different, yes. So in both cases, the direction is the same. The black bar is taller than the white bar on each side of the graph. But on the left, the black bar is only slightly taller, about 10 volts taller than the white bar. But on the right side, it's about, what, 40 or 50 volts. So the difference is not the same. So even though the direction is the same, black taller than white, the amount that black is taller than white is not the same. And so that's what the interaction looks like in this graph. So we have an interaction of those two things. And in this case, I think it's even easier to see that this particular combination of conditions is really different from the others. Because that one black bar, the one for people who were expecting alcohol and got alcohol, is so much bigger than all the other ones. So in this kind of graph, it's a lot easier to see that interaction kind of pop right out. That one special combination of conditions that mattered in this study. Right, so now let's think about our main effects. Main effect of beverage is going to be gray blob on the left and gray blob on the right. What do you think? Are those two gray blobs going to be different? Yeah, the gray blob on the right is going to be a lot bigger because it's got that whopping big black bar in it. So probably a main effect of beverage. And what about expectation? Black bars versus white bars. Yeah, the black blob is going to be a lot bigger than the white blob. So main effect of expectation. Whoa, here we go. Interaction? Yes. This is called a crossover effect. This is the strongest kind of interaction you can have. Okay, now, in a line graph, this looks very clearly, very clearly like an interaction. I mean, they're literally intersecting. Now, so we definitely got an interaction. Now let's think about the main effects. Here's where things get tricky. So let's think about beverage. If I'm trying to figure out if there is a main effect of beverage, I'm interested in slope, right? What's weird about the slope of these lines compared to other graphs we've looked at?
They're opposite.
They're opposite, right? One of them has a positive slope and one of them has a negative slope. What happens when you take a positive and a negative and put them together? They cancel out, right? So the slopes cancel each other out here, so we would say that there's no main effect because the slopes have canceled each other out. So this is an interaction, but there's no main effect of beverage.
Why do you just say a beverage?
Because I had to say main effect. And the beverage, we've said interaction, there's an interaction of those two things, but now we're talking about main effects.
Yeah.
And main effect is only about a single variable.
Okay.
Right? Main effect is about a single independent variable. And so I'm comparing, and if you want to think about it this way, if you want to imagine it another way, if I took that point up there and averaged the value with this point down here, it would be somewhere in the middle, right? And if I took that point up there and that point there and averaged them and put it, so it would be somewhere in the middle, it would be completely flat, right? So these two slopes are canceling each other out. So there's no main effect of beverage. Okay? What about expectation? We said we're supposed to look and see how far apart they are. On the ends, they're far apart, but what about the middle? In the middle, they're right on top, they're totally not far apart. So in this case, there's probably also no main effect of expectation. So this is an interaction with no main effects.
How does that happen though? Can you explain that? Like,
So this is an effect. Basically what this means is that people who, so let's look at the combination. So people who were not expecting alcohol and didn't get alcohol shocked a lot. The people who were expecting alcohol and got alcohol shocked a lot. So what this graph shows us is that if you got what you expected, you were mean. And if you didn't get what you were expecting, you were nice. Now, this is, I mean, although I think these kind of graphs look cool as line graphs, when you see them as bar graphs, it makes more sense that there are no main effects here. Okay, so let's think. If we think about, so the interaction, can you see it? In this case, the difference is the same, but what's not the same? The direction. On the left, it's the white bar that's taller, and on the right, the black bar is taller. So here we've got difference in direction. So that interaction is like popping out. Okay, because the difference is the same, but the direction is not. And to have no interaction, both have to be the same. All right, so now let's think about if we made this gray blob and this gray blob, would they be about the same size? Yeah, no main effect of beverage, because the blobs would be about the same size. Does that help?
Yeah,
In this kind,
that makes more sense.
yeah, this is easier to see it. That's why we do it both ways, because some people get it easier with the blobs, and some people get it easier with the lines. Okay. Now, what about if I added? So that would be the main effect of beverage, right? The size of the gray blob over here, and this, compared to the size of the gray blob over here, they would be the same. So no effect of beverage. If I think about alcohol, I'm thinking about the black bars combined together into a blob and the white bars combined together into a blob. Now, what would you get? It would be the same. No main effect, right? So this is one of the cases where I think it's actually easier to see what's going on when you have a bar graph than a line graph. And think about that. If you're ever presenting data, you want to use a graph that makes your outcome clear, not makes it harder to understand. And people are like, I love line graphs. And I'm like, because they're cool for interactions because you get to see the lines cross over. And I'm like, yeah, that's okay, but this makes it much clearer that there are no main effects, I think. I like this one better.
And you use colors.
Huh? And you get to use colors or patterns or whatever. It's more fun. All right. Oh, now we're going to switch it up. I'm going to switch it up. I'm going to change it so now instead of having a 2 by 2, we're going to have a 3 by 2. 3 by 2. And on your handout, I've given you both line graphs and bar graphs. We're just going to go over line graphs for this, just because I want to make a visual point. So I'm not going to talk about bar graphs for this one. Okay, so let's say I switched it up a little bit, and I actually made my categories for alcohol. Instead of having it be alcohol versus non-alcohol, I actually have different gradations of alcoholic beverage, and I actually measure blood alcohol content. So I want to take people who are sober, people who are impaired, legally impaired but not intoxicated, and people who are legally intoxicated, right? So these are distinctions that are relevant to the law, right? If you blow point 0.1, that's a DUI. You blow at 0.05, that's DWI, and that's very different, right, in legal terms. So we're going to switch it up to a 3 by 2. Again, random assignment between subjects for everything, so it's still a random groups design. It's just a 3 by 2 now, and now there are 6 conditions, right? 3 by 2, 6 different conditions. So take a look at this graph. Okay. Do you think we have an interaction? No, why not? They're not perpendicular. Perpendicular would be like this. Time out! I know that's what you want to take. In your head, you're like, stop! But no, we have to keep going. So they're parallel, right? They're not moving towards each other in any way. They are not touching. They are not crossing. Okay, so we have no interaction. Do you think we have a main effect of blood alcohol content? Yes. Why do you think so? Slope? Yes, that would be exactly why. So the lines are not flat. Can you tell me about that main effect of blood alcohol content? Well, could be. Yeah, we haven't done the math, so we're not sure. But you can describe it to me. There's a possible main effect of blood alcohol content such that what? People who have higher blood alcohol content give more intensive shocks than people who have lower blood alcohol content. If you want to be really good and make me really happy on the test, you would say something like, there's a main effect of blood alcohol content such that people with 0.1 BAC